Welcome to West Virginia. So, it's time for Joke of the Day, because it is the best part of the day. And here's today's joke. My brother, he didn't really like his beard, but then it grew on him. All right. And speaking of things growing on us, let's take a look at permutations, because that's going to grow on you. So permutations is a situation where we are trying to figure out how many combinations we can make, how many different arrangements we can make. But the restriction to permutations is that we are selecting objects from a set and we are arranging them. In other words, order is going to matter tremendously. The order in which we make these arrangements matters. And we've talked before about how when order matters, it feels like that restricts things, but it doesn't. It actually opens stuff up. So one of the ways that you can figure out that combination is to use this idea of a permutation. Here's the symbol for permutation. Whenever you see a P, parentheses, and a number here, comma, and a number here. What that means, the first number is going to be how many objects you've got. The second number is going to be how many you are taking at a time. Because sometimes you'll take all of them at once. Sometimes you're only going to take part of them. So this last number here tells you, here's how much I've got, here's how much I'm taking of the set. And this is just a different way to denote that symbol. You can either see it written this way or you can see it written this way. But either way that you see it written, what it indicates, the computation to get there, says I'm going to take this first number, the total number of objects that I've got, and I'm going to do a factorial of that. Now we've talked about factorials before. What that means is whatever this number is, I'm going to multiply it by a succession of numbers. Each of these successive numbers is going to be decreased by 1. But then in this denominator, what I'm going to do is I'm going to say, well, let's take all those objects and let's take out how many we are selecting so that I see what's left over. I'm going to do a factorial of what's left over so that it'll cancel out my total that's in that numerator, and that will leave me with whatever is left. So I know that's not making a whole lot of sense right now, so let's take a look at an example and then it'll settle in really well. The example says that we've got 12 students who are trying out for the trumpet section of All County Band. And those 12 students, we want to figure out how many different ways that they can be seated. Now notice what's happening here is I've got a total of 12 students who are trying out for this section. I'm taking all 12 of them. I'm not leaving anybody out. Now the arrangement in which they will sit matters tremendously. So order matters, but I'm not leaving anybody out. So if that's the case, then my permutation says that I've got 12 of them that are being selected. I'm taking all 12 of them at once. And again, a different way to denote that would be to say I'm taking 12 of them, permutation, 12 selected at a time. But what I just described here is the calculation for that says that I'm going to do 12 factorial over 12 minus 12 factorial. Now, you know that order of operations says do what's in that parentheses first. 12 minus 12 is 0, so what this really indicates is 12 factorial over 0 factorial. Now, we've talked before about what 0 factorial means. 0 factorial is just a 1. So really what I have is 12 factorial over 1. I don't need to show ones that are in the denominator. So really, in fact, this just simply means 12 factorial. So if that's the case, 12 factorial simply means I'm going to do 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And when I multiply all those numbers together, I get an enormous number, and that enormous number is 479,1,600 different ways that I can arrange these 12 students in the 12 chairs of the trumpet section, because the order that I arrange them matters tremendously. And so that tells me all the different combinations. Notice that I'm not listing all the combinations. That's entirely too many to list. But I do know what my options are. I have a lot of options for arranging those students. Now, let's take a look at another example And in this next example, what's going to happen is we're going to say, okay, let's take those 12 students, but we're not going to take all 12 of them. So in this situation, I'm arranging only some of the objects. So I still have 12 students who are trying out for that trumpet section of All County Band, but this time only 8 of them are selected. They are arranged first chair, second chair, third chair, and so forth. So the order in which I arrange them matters tremendously, and that leads me to know, okay, this is a permutation because order matters tremendously. But what happens in this permutation is I still have 12 students total, but this time I'm not selecting all 12 of them anymore. I'm only selecting 8 of them. So again, a different way to write that, just so you're familiar with the different ways, is to say I've got 12 objects taken 8 at a time. And the calculation for that formula says I'm going to take that first number, do a factorial of it on that numerator. On that denominator, I'm going to subtract the 2, because what I'm going to do is I'm going to say, well, just tell me what's left over. And I'm going to work with what's left over. So order of operations says that I'm going to do that subtraction first. And 12 minus 8 is 4. And that gives me 12 factorial over 4 factorial. So when I do 12 factorial, what that indicates, I'm going to change markers so this doesn't all run together. 12 factorial indicates 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 4 factorial indicates 4 times 3 times 2 times 1. And as I've discussed before, these 4s will cancel, the 3s will cancel, the 2s will cancel, the 1s will cancel. So like I said before, what's happening here is it's saying, let's remove the 4 left over that I'm not taking. Let's deal with those 8. Let's get them out of there so that I can see what's left over. And what is left over is simply 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5. When I multiply all that out, I get another very large number, but not as large. And let's make sure I got some room down here. I'm going to get a 19,958,400 ways to arrange those students. 12 of them, but I'm only taking 8 of them at a time, not taking all 12 of them. So you can see it does shrink the amount of ways that I can arrange them because I'm not taking everybody. So let's take a look at one more example, and then I'm going to kind of recap and see if you're noticing something with permutations. In this last example, we've got 7 boats. They are racing in the America's Cup Yacht Race. So these 7 boats will finish the race, and we want to know how many different arrangements could there be for how they finish. So what's happening here is I've got 7 boats. I'm taking all of them together at once. I'm not leaving anybody out. So that tells me that because the order that they finish is going to matter tremendously, that's a permutation. So I've got a permutation, and in that permutation, I've got 7 of those boats. I'm taking all 7 of them at a time. So once again, a different way to write that is to say 7 boats taken 7 at a time. And the formula says that means I'm going to take that first number, factorial on the numerator, and on the denominator, I'm going to subtract the 2 numbers and do a factorial of that. But as we said before, order of operations says do what's in that parentheses first. 7 minus 7 is 0. So I have a 7 factorial over a 0 factorial. And as we discussed before, 0 factorial is just a 1. And I don't need to show the 1 on the denominator, so this is really just a 7 factorial. And the definition of 7 factorial is that it is 7 times 6 times 5 times 4 times 3 times 2 times 1. And when I multiply all those numbers together, I get a 5,040. And so there are 5,040 different ways that these boats can finish, and the 5,040 different arrangements of their placement when they finish. So now what I want to do is I want to take a look back at these calculations and see if you're noticing something that happened. Say, for instance, in the last example we did, once we did all this and we kind of canceled everything out, notice what happened was basically we had 1, 2, 3, 4, 5, 6, 7 slots essentially. And so what happened was I had 7 boats, I had 7 slots. And I said, well, I've got 7 choices in that first slot, but once I do that, that boat can't be used again. I'm down to 6 choices in the next one. Once that boat is placed, I'm down to 5 choices in the next one. Once that boat is placed, I'm down to 4 choices in the next one, and then 3, and then 2, and then 1. Notice as well, let me flip back to this one, because it had a similar idea, that we had that 0 factorial down in that denominator that reduced that to just a 1, and we were left with just a 12 factorial. So what happened here is we said we had 12 students, so in other words, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 slots. And in the first slot, I could pick from 12 students, but once that student is selected, I cannot use that student again. I'm down to 11 choices in the next slot. Once that student is selected, I can't use that student again. I'm down to 10 choices in the next slot. And that's going to continue on for reducing it by 1 every single time. So hopefully you're kind of going, wait a minute, that sounds kind of familiar. And yes, it's very familiar. Take a look at this last example, and then we'll kind of settle in on what this sounds like. In this example, notice that when we did that 12 factorial and the 4 factorial in the denominator, and the 4 and the 3 and the 2 and the 1 canceled each other out, we were simply left with this. Notice I've got 1, 2, 3, 4, 5, 6, 7, 8 slots. But remember, I had 12 students, but I had 8 slots to fill. So in that first slot, I got 12 students to choose from, but once that student is selected, I cannot use that student again. The next slot, I've got 11 people to choose from. And in the next slot, I've got 10 people to choose from. And in the next slot, 9, and so on and so forth, all the way down the line until all the slots are filled. Yes, this is the fundamental counting principle. So permutations are actually just a form of the fundamental counting principle. So if we go back to each of these examples, what we can do is we can say, okay, in this example, I had 12 slots to fill. So instead of doing it this way, I could just say, well, here's my 12 slots to fill because I've got 12 chairs, 3, 4, 5, 6, 7, 8, 9, 10. Whoops, I'm making them too big. 11. And let's shrink it up a little bit. There we go. There's 12. And I can put 12 in here, 11 here, 10 here, 9, 8, 7, 6, 5, 4, 3, 2, and 1, and multiply all those numbers together, which is exactly what I had, what I just erased. It's the exact same thing. And so then if we flip it over, as well in our final example down here, again, like I said, I can say I've got 7 slots to fill, 1, 2, 3, 4, 5, 6, 7. And I've got 7 boats to choose from in this one, 6 then because I've placed that one, and then 5, and then 4, then 3, then 2, then 1. Multiply all those numbers together. That's your fundamental counting principle, but it's exactly this. And similarly in this example, when I say I've got 12 students, but I'm only selecting 8, that means I have 8 slots to fill. So when I have those 8 slots to fill, then what happens is I say 1, 2, 3, 4, 5, 6, 7, and 8 like this. In that first slot, I've got 12 people to choose from. But once that person is chosen, I'm down to 11. Once that person is chosen, I'm down to 10. And then I'm down to 9, 8, 7, 6, 5. Multiply all those numbers together. That's your fundamental counting principle, but notice that's exactly what happened here. So like I said, fundamental counting principle and permutations is very similar, and you can use either one whenever you are arranging, and order matters. That's the key, that order matters. All right, I hope you have a good day.